Okay, so this is everybody's favorite topic, significant digits. Now, significant digits is mostly used kind of like in theoretical science, like what we're in now. It's not really the practical, applicable kind of a science like engineering, where you need exact values in order for a measurement. As an example, we're dealing with these calculations on paper, but when engineers do calculations on paper, they need everything to fit exactly. For example, significant digits requires us to round to a certain number of um, precision or certain number of accuracy, but with the engineers, they want it to be exactly to as many decimal place values as possible. So if we're building a bridge, they got to make sure that bridge will fit exactly on the land and the spaces between the water. So in physics, theoretical physics, it's not really quite the case. So a lot of this won't make a whole lot of sense, but just know that it's for theory applications rather than practical applications. So there, when we talk about significant digits, we got to talk about accuracy and precision. Now, accuracy is the degree of closeness of a measured or calculated quantity to the actual or the true value. What that basically means is that how accurate you are is how close to the reference value it happens to be. So if you have something that weighs 1 kilogram, how accurate your measurement is always related to how close your measurement is to what another object that's exactly 1 kilogram. So, for example, there are these vaults in, I believe, in Paris and somewhere in Washington, and they have these masses that are exactly 1 kilogram, and there are these meters sticks that are exactly 1 meter, so on and so forth. So it has an exact measurement that you can compare your measurement to. Now, what precision means is how many digits you can carry out a particular measurement. The more digits you can carry out, the more precise that value is. So, a popular analogy that I often see in physics would be the arrow and I guess arrow and a target. And so the bullseye will be the center. If you can consistently hit that a bullseye, it's more accurate. Now, and so basically, in essence, the closer the measurement is to the accepted value, the more accurate that measurement is considered to be. Now, what precision basically means is that if you fire 10 arrows and all the arrows would be in the same spot or very close to the same cluster, then we call that it's very precise because you're always very consistently hitting the same area. But that's just an analogy. It's not exactly a perfect fit, but that's kind of like the differences between precision and accuracy. So if you look at this chart, where you have this area here versus this area here, okay? So if you have this bullseye here, if you notice all the arrows are all over the place. So you have low accuracy and low precision. Whereas over here, you have high precision because they're all in the same cluster, but it's pretty low accuracy. Whereas over here, you have pretty good accuracy but low precision because all these arrows are close to the cluster in the center, but it's kind of scattered throughout. And this example is pretty much precise as well as accurate. So here's an example of accuracy. If a true value of a particular measurement is 2.001 meters, and you measure the same item as 1.9 meters, another student measured the same item and got the result of 1.894 meters. Between you and the other student, who had the more accurate measurement? So it might be a good time for you to pause, think about it, and see what you can come up with. So if you had said that the other student is more accurate, you'd be wrong because 1.9 meters is definitely closer to 2.001 meters than 1.894 meters. So that means you you have measured 1.9 meters, you're more accurate because it's closer to the accepted true value of a particular measurement. Now in the same example, except you got a third student measuring the same item and got 2.1 meters. Now, which of these students are now more precise? So remember the previous question was accuracy. This is now precision. Now take a moment, think about it, take a pause, see what happens. So you had guessed that you were also more precise, you would be wrong. In fact, the more precise something is the more digits that measurement can be carried out. So 1.894 meters is basically the more precise measurement. So a measurement could be more precise but less accurate. So that's a kind of a conundrum. So that's kind of confusing. So if you have any questions, remember to ask again when we have group discussions. So now it brings us to the question, what exactly is a significant digit? And significant digits is, again, theoretical, where the number of these digits will carry out some sort of meaning to its accuracy. So some accuracy can only be lent itself to a certain number of digits, so we have to keep that level of accuracy consistent. So as a general rule of thumb, the answer from a problem cannot be more accurate than any other part of the problem. So again, answer of the problem cannot be more accurate than any part of the problem. So if you have 3 terms and you're adding them together, the answer cannot be any more accurate than the any parts of the problem. So there are 4 rules. You gotta remember these 4 rules, and all these rules can and will be applied towards significant digits when you're looking at a particular value. Different rules are used when you're adding, subtracting, multiplying, and dividing. So let's go over these rules. Whenever you have a non-zero digit, that means any digit that's between 1 and 9, they're always significant. When you have zeros that are placeholders, they will never be significant. So if you have a 0 that's in the number 100, 100, 100, the 2 zeros are placeholders and they are never significant. Now if you have zeros between significant digits, then those zeros are significant. So as an example, 101, that 0 is between 2 significant digits, therefore it makes it significant. And any final zeros after the decimal point, they're always significant. So if you have a measurement that's 100.00, okay, that final 0, because it's the final 0 after the decimal point, it's significant. And all those zeros between the 1 and the final 0 in this value, in this measurement, those are also become significant because zeros between significant digits are significant. So you can see that all these rules can be used simultaneously. Okay, so here are some examples. Let's look at 1 through 7 and see if you're able to get the correct answer. So go ahead, pause this video, and then go ahead and write them down in your notes, as I assume you're all taking notes, right? If not, start over from the beginning and start taking some more notes. Okay, so go through 1 through 7 and see if you're able to come up with the correct number of significant digits. And we'll check it over tomorrow in class. So, well, you can pause it, so we'll move on. So when you're adding and subtracting values when utilizing significant digits, the rule is when you're adding or subtracting numbers, the answer must be rounded to the least precise place value from the parts of the problem. So if you look at the example here, 9.50 meters plus 11 meters, you will notice that there are 2 parts to this problem. Term 1 is 9.50, term 2 is 11 meters. So you need to look at, again, you see the big, bold thing here, least precise place value. So between 9.50 and 11, when we talk about precision, is the number of digits that's carried out as far as you can to the right. So if you look at 9.50, this is precise to the hundreds place. and the 11 is only precise to the ones place. So between 9.50 and 11, 9.50 is more precise than 11. So when we add the values, we have to round the answer to the ones place, which is the least precise. So when we add 9.50 plus 11, we get 20.5. Keeping the units the same, leaving at the meters. We look at this number, 20.5. It's not significant. So we have to round it to 21. Remember, rounding is 5 or higher, round up. Lower than 5, round down. Okay. We're multiplying or dividing significant digits. Yeah, this is my division sign. I couldn't find it on my computer, so I have dots and stuff. So anyways, when you're multiplying or dividing numbers, you round the answer to the value from the problem with the least amount of significant digits. This is where those 4 rules for significant digits comes in handy. So if you're multiplying 100 meters times 5.5 meters, you'll really need to know how to determine the number of significant digits, because for multiplying and dividing, we're looking at the least amount. Okay, so 100 meters times 5.5 meters. 100 has only 1 significant digits because these zeros here are placeholders. 5.5 has 2 significant digits. And so when we multiply 100 times 5.5 really is 550 meters, but we need to round it to 1 significant digit because this part of the problem here has the least amount of significant digits. So we round it to 600 meters squared. Remember, the meters, the units, must also be multiplied together, giving us meters squared. Okay? Now, when you're multiplying and dividing, this rule applies to squaring or square rooting and processes like that. Okay? Now, here are some practice problems for number 8 through 13. This is where you want to pause and try to work out these problems. See if you can use, don't use your calculators and just do this, by hand, because this quiz this Friday, we will not be able to use any calculators. So if you look at this math, it's generally pretty easy. You can add and subtract these fairly quickly. So go ahead and work off of that. Now, number 12 and 13 requires you to know some basic math using scientific notation. So if you haven't done so already, you might want to go back and look over the scientific notations lecture notes. So pause, try it out. Have any questions or want to check your answers? We can do that during the study session. Not the study session. I'm sorry. The group discussion on Tuesday and on Wednesday. Okay. All right. Good luck.